All right, we are on to astronomy, which is the topics we're going to cover today. We're on the last unit, and today we're going to cover the solar system. In other words, the area around our own sun, and then we're going to broaden that into stars and galaxies and the scales that we're going to talk about. In other words, the sheer size of the stuff that we're going to talk about today may blow your mind in the end, okay? But hopefully that'll be the case, because I think it's kind of cool stuff. But astronomy, I've said this about a number of topics this whole term, and astronomy is one of those topics, again, that you could spend your entire career studying. Most people who end up in astronomy do an undergraduate degree in physics, and then maybe at the end of their undergraduate degree they kind of broaden into some astronomy. But astronomy, generally most of your astronomy classes happen at the graduate level, and it gets really math heavy. I mean, like super duper math heavy. Many astronomers these days don't even deal with actual light coming, well, visible light coming from stars and things. It's all like radio astronomy or X-ray astronomy, or basically they download a whole bunch of data collected from these giant telescopes that listen for radio waves or X-rays or even visible rays into computers, and they manipulate them, and then they can, using that data, they figure out cool stuff about the universe. Because outside of the moon, humans have been to no other place except Earth in the universe, right? So we, yet. Now, we have sent rovers to places, and we have sent other satellites and things, which we'll talk about tonight. But as far as the humans themselves go, it's tough to actually get somewhere and actually, do a real experiments, standing there. Of course, the other issue is, how do you actually study things up close if they're things like the sun? You know how we study the sun up close? How we get up close? We just go at night. Yeah, no, I'm just kidding. Yeah, I know. No, but anyway, the point is that we do a lot of this stuff remotely, as is necessary, and a lot of it involves digging through a ton of data to do it. That doesn't mean to say there's dry stuff. It's very fascinating. In fact, all this stuff tonight, I think, is some of the cool stuff we've studied all year, and a lot of it builds on the previous stuff. Okay, I mean, you really get into physics when you're talking astronomy. You do get into chemistry. You do get into earth science is probably the wrong term, but you get into like planetary science and what makes up the elements and minerals and so forth. And then, of course, you've got all this other stuff that goes along with the fact that we live in this huge universe with lots of stars and lots of planets and lots of stuff that we'll talk about. Okay? All right. So astronomy is a natural science, deals with the study of celestial objects, in other words, objects outside the Earth, such as moons, planets, stars. Well, I should say, so we are a celestial object, the Earth itself. Just we don't really necessarily normally think about that. We are located in outer space, right? Like the planet Earth is on its own out here, except for the moon, 300,000 miles away, and then, of course, the sun, 93 million miles away, and other planets and so forth as well. But we're in space, right? We used to study astronomy using the naked eye. In other words, you used to look up and you saw things like constellations, and you saw the moon, and you saw planets, and and all this with your eyeballs. But when Galileo came along and started using this newfangled thing called the telescope, he looked up and saw all sorts of other stuff that you couldn't see with your eye, right? Which, in particular, he's the one who noticed there were moons around Jupiter. Okay, he noticed the 4 biggest moons around Jupiter. And by the way, a lot of astronomy throws a big wrench into some of the things that a lot of religions teach, much like the age of the Earth and so forth. But because, for instance, when Galileo came up, saw these moons going around Jupiter, well, traditional thought was that everything revolves around what? The Earth. So if there's some other planet out there that's got other stuff revolving around it, something might be not so special about the Earth. So that brought up some, controversial issues. Okay, and Galileo ended up, because of some of these controversial issues, spending a lot of time in house arrest, which didn't help his career particularly. Kind of made him a little bit annoyed. But anyway, so once we use telescopes, we realize there's a lot more stuff out there, stars, planets, etc. And that type of astronomy lasted for many, many years until the 20th century, when we had the ability to collect radio waves and X-rays and gamma rays and infrared rays and UV rays and all the stuff you can't see, and realized that all these stars were producing a lot of this stuff as well. In fact, other things besides stars produce some of these things. So then we started collecting on those. So astronomy, like I said, is a huge, huge topic, but part of it is because we have all these great tools to gather data that is being bombarded onto the Earth. Oh, including, by the way, neutrinos, which are tiny little itty-bitty particles that have almost no mass, and most fly straight through the Earth when they hit us, and they're used to determine where certain stars and other bodies are. So kind of cool stuff that we use to do a lot of this astronomy. Okay, we're going to begin with the solar system, our sun, 8 planets. Anybody want to try naming them? Earth, Mars, Mercury, Venus, Saturn, Uranus. That's the way we're going to pronounce it in here. Neptune, Jupiter. That's 8. What's not a planet anymore that we're all sad about? Pluto, right? Okay, there is another. There's plenty of those. Pluto is now considered a dwarf planet, which is kind of a nice way of saying, hey, you don't really count as a planet. But there are many of those out there, and that's one of the reasons Pluto ended up being declassified as a planet. Was, are we going to classify everything that's out there as a planet that happens to, be kind of bigger than an asteroid and goes around the sun? No, we're not going to. So Pluto kind of lost the bet on that one. Okay, so once we get past the solar system, we're going to branch out the rest of the galaxy and other galaxies. Now, planets in our solar system are divided into 2 classes. Number 1, we've got the inner planets. Okay, starts with Mercury, which I think this is to scale, meaning that the planets themselves, the size is to scale. The distances are certainly not to scale. But you can see tiny little rock right there. That's Mercury. In fact, Mercury is smaller than some of Jupiter's moons. Okay, I mean, it's pretty tiny. Still classified as a planet, but pretty tiny, all things considered. Then we have Venus, then we have Earth, then we have Mars. Those are the inner planets. They are rocky. Okay, they're mainly just like Earth. They are mostly rocks. Then you have the outer planets, which are called the gas giants. They're gas giants because they are generally not made of rocks. Okay, they're made of primarily gases like hydrogen and helium and so forth. There are solid parts of these gas giants. In fact, Uranus and Neptune are completely frozen, as far as we know, but they're still considered gas giants because the elements that make them up would be gases in normal, like room temperature kind of situations. But anyway, inner planets, outer planets. Okay. And as I said, these are the relative sizes. The sun, look at how huge it is. This is like 98% of the mass in the entire solar system is the sun. It's gigantic. Okay, it's huge. Okay, Jupiter is also pretty big, not nearly anywhere near the size of the sun, but still pretty big. Saturn's big, but then it's actually bigger when you consider the rings. Some of the other gas giants also have rings, incidentally. But our planet and these other inner planets, pretty tiny. Okay? Now, when we talk about the size of things, I was going to put this on later in the brief when we talk about star sizes, but I think it's interesting now. I'll show you a little video that talks about the sizes of some of the other objects in our galaxy. Okay? And this hopefully will impress you. If I can find it. Back video. Star size comparison. Here it is. Okay. I think some guy made this up on his computer, but tell you what, Eric and Tom, you want to hit the lights? Oops. So the moon's already kind of big, right? The moon is not tiny. There's Mercury and Mars. It's pretty dramatic music too. Okay, Venus. Venus is almost the same size as Earth. All right, there's Neptune. Okay, Neptune's pretty big. Saturn with no rings, pretty big. Keep in mind, you can barely see Earth. Jupiter. All right, this is the biggest thing in our solar system, the sun. There are other stars. Sirius A. Pollux. That's an orange giant. Anybody ever heard of a red giant bigger than Arcturus? Not that you would have heard of Arcturus necessarily, but Betelgeuse? That might be next. This is another bigger one. So we're getting there. These are pretty big at this point. Remember, this... That's our sun. No, that's our sun. That little tiny little dude right there is our sun, right? So there's 1, 2, 3, and then this guy, bigger. We're getting there. Another red giant. Blue supergiant. A blue hypergiant. Oh, guess what? There's another red supergiant. Oh, maybe another one. Oh yeah, that's not it. That is the biggest known star. You can't even see the sun or anything. I mean, we're talking like very big. I don't even know how to put it. Right? So how do you even figure out how big this size is? 2.8 billion kilometers. No, sorry, yeah, 2.8 billion kilometers. Think of a passenger airplane flying on the surface. So you're in your passenger airplane. How long would it take to go around the Earth in an airplane? Any idea, roughly?
80 days. Depends on how fast we're going.
Depends on how fast you're going, but let's say around 600 miles an hour. 80 days in an airplane?
Yeah, around the world.
No, around the world, around just the Earth. Well, you get from here to like...
Wait, what's the circumference of the Earth? 70 days?
The circumference of the Earth is, what is it, 30,000 miles or something like that, roughly?
Okay.
Anyway, 900 miles an hour, 30,000 miles, 900 goes into 30 what? 9 goes into 30 about 3 times 3, 30. So 30 hours or so to get all the way around the Earth. It would take years, 1,100 years to circle this sun, or this star. That's pretty darn big, okay? And by the way, tiny compared to a lot of other things, which we'll get to later in the thing, okay?
We're the only one with intelligent life on it, right?
No, you aren't the center of the universe. Okay, so, well, we might not be alone. We'll talk about that as well. But okay, hit the lights on if you would. Yeah. Let's see.
I think it's funny when people say that. Oh yeah, we're the only ones with intelligent life. Yeah, okay, whatever.
Well, we'll talk about whether or not we're intelligent life. Probably Monday. Okay, so that's the size in terms of some of the objects in the universe. We are, even the Earth is pretty small. Even the sun is pretty small compared to some of these other huge objects in the universe, or in the galaxy even, okay? Let's talk a little bit about distances in our own solar system. If you go from the sun to the Earth, okay, it's about 93 million miles. We call that 1 astronomical unit. Why? Because we think we're special and we're Earth. So that distance from the sun to the Earth is 1 astronomical unit. Okay, so if you look on this little chart here, it's a distance from the sun. Mercury is 0.39, about 4/10 of the way to us from the sun at some points of the year. Remember, if the sun's here, Earth can be here and Mercury could be here, or Earth can be here and Mercury can be all the way on the other side. So depending on where you are in the orbit, you can be a long way away from some of these other planets. But anyway, 0.4, 0.72, 1. We're 1 astronomical unit away. Mars is 1.52. These are the inner planets. To get to Jupiter, you have to jump all the way to 5.2. Okay, Saturn is a whole other jump of about 4.5. Uranus, you double the distance more. You more than double the distance to get to Uranus. More than double, well, about another 2/3 of the way farther, you're at Neptune. So we're already pretty far out there. And then Pluto is even farther, and then this Eris, which which Louis mentioned earlier, is out there even farther. Okay? The question is, let's talk about scale in terms of our planets versus the distance away from the sun, like the size of the planet versus the distance away from the sun. Okay? I've got another thing. I'm going to switch here to a different picture here, and this should give you a little bit of an idea. Let's say that the sun. Let's say we modeled this as the sun being about a little bit taller than this building. Okay, so think about it as being pretty wide and pretty tall, but about that big. Okay, Mercury would be about I think 1/10 of a centimeter or 1/2 a centimeter, about that big. Okay, how far away would it be? Well, does anybody recognize where we are here?
Yep.
We are at Camp Lemonnier. Let me zoom out a little bit here. Let's see if I can. I wonder if I can do this. I wish I could make this smaller because it's not the best here. Let's see. I guess I can. I can't even move that. Well, anyway, you guys can see that here's the runway, here's the airport, here's Clouville, right? Let me zoom way in. And OK, so now you got it. That's Clouville down here. And then the turf field is right here. Everybody see the mouse around right here? OK, good. OK, well, if we go over, let's go in a little bit more. Satellites these days, I tell you. Anybody can get this online.
Yep.
OK, let's see. Chow Hall, Old Chow Hall, Thunderdome, and then us. OK, so right here, in fact, that star is about the size of the sun in this case. That little star right here. OK, see that's us? That's like this trailer right here. Boop. Someday it'll be real life, so you'll be able to go out and wave. Right. Just a satellite picture, not live.
Yeah.
It's not live right now. What's that?
Real-time video.
Real-time video, exactly. So anyway, if that's the sun, okay, let's look at where Mercury would be. Mercury, I'm going to have to zoom out a couple times here to do this. Mercury would be right there, which is not easy to see in this. Mercury would be there at about 0.13 kilometers. So right about the edge of camp is where Mercury would be. Okay? All right. And by the way, if you go to a city like Boston, some of these cities have real-life like demos of this thing where they like the Museum of Science has a building where they say, here's the sun, and it's like roughly the size of this building. Actually, it's a little small, a little bit bigger, I think. And then they go out to the distance away from the museum where the things are, and you can go on this little like, it's like a treasure hunt. You go out and you find it, and it's all around the city of Boston, and it keeps going out. Anyway, if we were to do it, we could put Mercury right there. So let's go to Venus, which would be next. Let's zoom out a bit again. Venus is now, let's see, Venus is, let's see, here. So here's Mercury, see where that green dot is? And then if I go down, that's where Venus is. So from like here to here is Venus. OK? All right. Earth, bing, right about there. So Venus to Earth, not too far. We're actually, let me zoom out a little bit more. OK? Venus, or Mercury, Venus, Earth. Okay? Yeah, almost. A little bit, not quite equal distance, but kind of far away. This is about 1/3 of a kilometer away. Not too far. Mars, from there to there. Mars isn't too far away either. Okay? All right, let's go on to the outer planets. Okay? We go to Jupiter, we have to go a pretty fair amount of way. See that jump? Let me zoom out again. Let me zoom out a couple here. OK, so can you see the green still? Yeah. So there's, let's see. So we go Mercury, then Venus, then Earth, then Mars. So Jupiter is way out there. So you see that jump? It's a pretty good jump from here to, from like there to there. Okay. Saturn is next. Saturn, bing, another big jump. Now we're really jumping. Can't even, I got to zoom out again for this one. Right? Saturn is there. OK, I'll go a little faster here. So we've got, let's see. What was it? Yeah, there we go. So that's Jupiter's there. Oh, there's no dot anymore, is there? Oh, no. I might be too far out. Hang on, let me zoom in a little. There we go. OK. All right. Jupiter, Saturn. Uranus is a big jump. Boom. See that big jump? And then Neptune is another big jump. And then finally, if you want, we can go to Pluto, which is even another big jump out to there. So let's look at the whole thing. So that's about 13 kilometers away. So if that was the size, if the sun was as big as this building, or well, as tall as this building, right, you'd have to go all the way to 13 kilometers away from the city of Djibouti just to get to Pluto. So it's a pretty big distance for the size of planets. Our galaxy is almost empty when it comes down to it, right? It looks like, hey, the sun's out there and it's making everything bright and all that, sure. But really, you can go for a long way before you hit anything. And in fact, if you tried to hit something without knowing exactly where you're going, you'd never hit anything. It's just too much space. It's kind of similar to if you've ever sailed on the ocean. I mean, people sail solo, like literally go on a sailboat, like 25 feet long, and sail solo around the world, and they sleep for, not normal hours. They get up, some people get up every couple hours or every hour or whatever. Some people sleep for like 6 or 7 hours, and they have radar, and they have, hopefully, GPS and whatever, to keep them kind of, to kind of say where the other things are. But a lot of people do this without any radar. And they just figure, I'm in the middle of the ocean, the odds are I'm not going to hit anything. Same thing with space. You can go a long way without hitting anything. Now, if you were to try to go between star to star to star, you would, you probably would do that. You'd be in trouble. OK. So those are the distances. OK. How did our solar system form? Okay, well, we've got this theory called the nebular theory. Okay? The nebular theory says that the sun and the planets formed from this cloud of gas and dust called the nebula. Where did the nebula come from? Some other star exploded. Okay, some other star exploded in a thing called a supernova, which we'll get to much later in class. Okay, created all this dust and whatever, ended up in this part of the galaxy, and then it started to coalesce and come together because of gravity. The sun came together in one giant piece in the middle, and all planets kind of coalesced in their own littler pieces around it. Okay, nebula. What happened was we had this gravity. When pulled together, okay, for instance, the sun, however the particles are spinning around, when they come together, they spin together as well. They keep spinning based on this thing called the conservation of angular momentum. We talked about some conservation laws like 20 chapters ago, like energy and momentum. There's a conservation of angular momentum, which says that things that are spinning, unless they've got some external force, the whole object is going to keep spinning with the same amount. Now, you've all seen this before. Ice skaters, right? Ice skaters, they do this thing where they start spinning, right? And then they pull their arms in, and what happens? They get faster and faster and faster. It's the same sort of thing. As the slowly spinning particles come together, the closer they are to the center of what's spinning, the faster everything will end up going. So that's how we get things like the sun spinning and the Earth spinning and all these other planets spinning around. Okay? So it does this. Now, it also generally ends up, at least the solar system generally ends up in this disk shape. Now, by the way, this disk shape, the planets going around the sun, they are generally in the same plane around the sun. In other words, they're all kind of in this plane going out from the sun. Why? Well, it has to do with this idea of everything coming together, angular momentum being conserved, and it flattening out into this disk as it comes together. It's kind of cool. I mean, you'd think, why isn't it that we go this way around the sun and maybe some other planet goes this way, right? It doesn't work that way. They all kind of go on the same plane around the sun. Kind of cool. Okay? All right. The center of this disk, at first, it's what we call a protosun. Why do we call it a protosun? Well, for two reasons. Number one, it hasn't fully formed into its final shape. Number two, it's not bright yet. It has no light emanating from it yet, okay? Because it hasn't ignited, okay? And that ignition is when we start to call it a sun, okay? Outside here, we get these planetesimals, which are little baby planets that haven't quite formed yet either, okay? Once they get more material, they end up becoming planets themselves, okay? All right, check question. A nebula shrinks under the influence of gravity. Does it spin slower, faster, lose its spin, or spin into a protosun? Spins faster, okay? Spins faster, yeah. Oh, I don't know what happened with our font there. That's weird. Anyway, fine. So conservation of angular momentum is what causes this. Okay? Like a skater. Spins inward. Okay. So our sun. Okay, actually, before I even show you this, let me show you. I was told I had to show you this. It's going to be just a sec while I set this up. Let's see. Hang on. 11. Hopefully we can hear this. Oh.
Whoa, nice one, Simba. Thanks.
Bye-bye. Anyone know who this is? What movie this is? How'd you know that? Because you watched it. What was it? You watched it last night? Do you remember this scene? Did you think, hey, we're going to study astronomy tomorrow?
Said they're gases.
Let's see. Hang on.
Firefly.
Hang on. There we go. Don't ruin it. No, okay.
Whoa, nice one, Simba.
All right, hold on. Let's turn the lights off. Hold on.
I'm stuffed. Me too. I ate like a pig. Pumbaa, you are a pig. Oh. Right. Simone. Yeah? Ever wonder what those sparkly dots are up there? Oh, I don't wonder. I know. Oh, what are they? They're fireflies. Fireflies that got stuck up in that big bluish black thing. Oh, gee. I always thought they were balls of gas burning billions of miles away. But with you, everything's gas. Simba, what do you think?
All right.
Well,
We don't need to worry about what Simba thinks. All right. The light's back on. So guess what?
He was right.
The sun really is, right? The sun is a star, and the sun is a giant ball of gas. Now, it is not fire as we normally know it. Okay? The sun is actually a giant nuclear fusion bomb, really. Okay? What's causing the fusion is the amount of gravity. So the only way some proto-sun can actually become a sun is if it keeps gaining mass and becoming more and more and more massive. Well, the amount of mass pulls in closer and closer and closer, shoves those molecules of hydrogen together fast enough and hard enough with enough pressure such that we get fusion, which, as we talked about a few chapters ago in chemistry, is a process by which you get energy out of, right? And that energy that comes out of all that fusion is light and gamma rays and other kind of energy, right? So we get that from the sun. Now the sun, much like our Earth, is made up of lots of different layers. Okay? In the inner core, this is where all the magic's happening. That's where all the fusion is really happening. Hydrogen is becoming helium. Okay? It's going so fast together, it's fusing into helium, leading to the release of all this energy. After that, we've got all these other zones. We've got a radiative zone, a convection zone, convection being just like any other convection where you've got lots of movement of plasma. Plasma, by the way, you've got solid, liquid, gas, and then plasma, which is what the sun is mainly made up of, which what it means is the atoms are going so fast they can't hold any of their electrons anymore, and they're all just basically a bunch of protons flying around in this other form of matter. Okay? Then you have the photosphere here, which is the part that you actually see, well, mainly, when you're looking up at the sun. Then you've got the chromosphere, okay? And we'll get into the details of that in a minute, but the chromosphere, chromo being color, that's where there's some very colorful parts of the sun there. And then you've got the corona, which is this outside area of the sun, which goes way outside the sun. And it's filled with lots and lots of particles that are getting basically blasted away from the sun. Remember, it's like a nuclear bomb, okay, that's going off. Okay? A couple of things about the sun. Obviously, it's the nearest star to us. Okay? There's 100 billion other stars in the galaxy, so it's not particularly unique in some sense. Mostly made of hydrogen in this plasma phase. Okay? We already talked about the hydrogen fusing to helium in the core. Okay? There's about 4.5 million tons of hydrogen turned into energy each year. Sorry, not each year, each second. 4.5 million tons of mass converted to energy each second. So you'd think, well, the sun's going to just kind of disappear, right? Well, in some sense, it's losing lots and lots of mass, but it has lots and lots of mass to lose. I mean, it's kind of like saying you're losing mass every time you, like, you know, flick off a little bit of your skin, right? I mean, it's not going to, you could do that all day for like a long, long, long time before it would matter. Same thing is true with the sun. It is technically getting less and less matter every second because of this energy. And by the way, who benefits from that energy? We do, because we're the ones who, you know, get the energy from the sun. And that energy transfer is what keeps us alive, right? Some of that energy sustains the Earth. OK, a couple facts from the sun. The core, 15 million degrees. You don't want to go there, right? Pretty freaking hot, right? 12 times as dense as lead. So you think lead is pretty heavy and dense. 12 times more dense than that is the sun. And by the way, that's nothing compared to some other objects we'll talk about. Okay? Pressure in the core, 340 billion times air pressure. You would not last very long there. But that's why we get the fusion happening. One of the problems with creating a fusion reactor on the Earth, you know, we've got fission reactors that are nuclear reactors, nuclear power plants. We would like to create a fusion reactor. Why? Because the byproducts are helium and water. No big deal, right? Well, helium, basically. And it's hard to do because the pressures involved need to be immense. Getting things to that pressure are huge. The only way we can get that much pressure in order to blow up a hydrogen bomb is to first blow up a regular atomic bomb and then compress the other hydrogen so that it explodes into a bomb. Okay? It's tough to do. Sun definitely spins on its axis, okay? But it doesn't spin as a whole like the Earth does. It's a fluid. So the equatorial region around the middle actually spins faster than on the edges. Okay, so there's the difference. That difference in spin is actually what causes those sunspots that you might hear about or you can see in pictures of the sun. Okay, we've also got the surface of the sun, which is the photosphere part you can see, is only about 5,700 degrees. Only. I mean, you know, that's still pretty hot, but compared to 15 million, it's definitely cooled down some by the time it gets there. Still pretty hot, but not too bad. But after the photosphere, you've got this chromosphere, which I'll show you, I think I got pictures of, which goes back up to about 10,000 degrees. And keep in mind, part of the reason the temperature goes up is because there's less particles there, which just means they spread out more, so they're actually higher temperature, et cetera. Okay? And then the outermost region, which is that corona, goes out for millions and millions of kilometers. And that's the part that you can see when there's an eclipse. And I'll get to a picture of that in a little bit. Here's the chromosphere. This little part out here, see how pretty it is? Nice and pink and red and all that. That's the chromosphere. Okay? And by the way, this is during an eclipse. That's how you can see that. The corona you can really see during the eclipse. And actually, this is perfectly good to look at. If you happen to be able to see a total eclipse, I've never seen it. I would love to. I was just looking. In your book, there's a little chart that tells when the next eclipses are. There's one that goes right through the US in maybe 10 years or 12 years or something like that. Totally want to see that. Hopefully it'll happen on a day where wherever I go, it's sunny. It'd be kind of a pain to miss it because it's cloudy or something. But anyway, corona is seen during eclipse. You can see that whole area out there is the corona. As I said, this is perfectly fine to look at during an eclipse. And if you go somewhere where they've set up like telescopes and things to look at this, they'll broadcast when you can start looking and when you have to stop looking. Because the instant the sun kind of goes out of it a little bit, you don't want to be looking anymore. You might hurt yourself. You can wear special, like, very dark glasses to see that. But if you want to see with your naked eye, you can perfectly look at this if you do it at the right time, right then. You can take pictures of it and you can see that. OK, here's another check question. Strictly speaking, in every second, the mass of the sun decreases, remains constant, increases, or reinvents itself? Does it reinvent itself? What do you mean by reinvent itself? I'm not sure what that means.
Should I say remains?
The mass of the sun, remember how it decreases? We're losing all that energy to us and to the rest of the solar system? It has a lot of mass to lose, but it is losing it. Yeah, it is losing mass. It is decreasing. So don't, again, weird font change. Well, anyway, it does decrease in mass, but it's got so much mass. It's been burning for about 5 billion years. Well, 4.5 to 5 billion years. Probably going to keep burning for another 5 billion years. Okay? At that point, what's going to happen is the sun is actually going to, what's going to happen is the hydrogen that's there now, it's going to deplete all the hydrogen and become helium. And when that happens, the helium has to start fusing. And the helium fuses into whatever's next, lithium, or maybe it goes into carbon directly or something like that. But it fuses into the next thing, which fuses into, eventually into lead. And that's when it starts fusing. But in that process, because of the pressure involved with the gravity versus the pressure involved with the fusion and the explosions, the sun actually will expand into a red giant for a fair amount of time. By the way, it'll probably just about come out to or actually overcome the Earth, so we'll be gone. Earth will be gone, right? 4.5 billion years from now, or 5 billion years from now. And then eventually it will burn out all the way up to lead until there's no more burning can happen, and it will our sun will actually shrink back down into what's called a white dwarf star, and basically fizzle out at that point. Be really not very bright anymore, and it'll fizzle out. So lots of interesting things are going to happen to our sun.
Are all these speculation or?
Well, it's speculation. When we get to the next chapter, we're going to talk about stars in general. By observing other stars that are very much like our sun, and by observing other stars that the process that it goes through, we can tell probably what's going to happen to our sun. Almost certainly what's going to happen to our sun. So that'll do it. Tell you what, before we go to the inner planets, let's take our first break, and then we will come back after that. All right, so we talked a little bit about the sun, the energy-producing body in our solar system. Now we're going to talk about the inner planets, those 4 rocky inner planets that are composed of Mercury, Venus, Earth, and Mars. Here's roughly the size. This is an eclipsed view of Mercury. Okay? As you go farther away, the speed of your planet actually decreases. Okay? Now, what that really means is that Mercury does not take very long to get around the sun. Venus, a little less time. Earth, 365 days. And Mars, even less time. Okay? The farther away you go, the slower it goes. And, by the way, the farther distance it has to go. So they kind of combine. Let's start with Mercury. Okay, as we know, it's the closest to the sun, and it has a very weird day. I didn't write it up here, but the time it takes to go around the sun is actually similar to the amount of time it takes to revolve on its axis. What this means is, so let's see, the day on Mercury, like in other words, how long it takes for one day to happen, is something like 60 days on Earth or something like that. Like your day is long. Okay, it's very long. It might say in there. How many? 88 days per Mercury day, is that what it is? Or how long does it take to get around the sun?
Circling the sun in only 88.
There you go, circling the sun in 88 days. But it's like, how many, does it say how many days to go around its axis? I don't remember if it says. I thought it did.
3 times for each 2 revolutions about the sun. Okay.
So you have 3 days during 2 times around the sun. So 2 years on Mercury is equal to 3 days on Mercury. Okay? But what that actually means, this is kind of cool. Well, it depends how you think. If you like the day, right? You watch the sun come up, and now it takes a long time, right? And then because you're also going around the sun, at some point the sun actually goes, I think I'm going to go the other way for a while. And then it finishes by going all the way around. right? So your day looks kind of weird. The sun comes up, goes down a bit, and then goes all the way around again. So it's kind of weird. But what this also means is that in the day, which is like 80 days long, well, whatever, 2/3 or whatever, 60-something days long, gets hot, 430 degrees Celsius. So it just bakes the crap out of that planet, right? Just bakes and bakes and bakes. Nighttime, though, also very, very long. And on the other side of the sun, negative 170 degrees Celsius. So if you think the temperature swings are big on Earth, try going to Mercury, right? No atmosphere. It's too small. It's pretty close to the sun. Atmosphere burns away. If it was any, no atmosphere. Okay? We have sent satellites to orbit around Mercury. Okay? So we've got lots of cool pictures of Mercury. Not much to them, really, because it's just a big rock. Okay? Venus. Now, Venus, the second planet from the sun, is pretty close to Earth in a number of ways. It's got a very similar core. It's got a very similar composition, I should say. It's about the same size. It also has volcanoes. But Venus has actually suffered from global warming, basically, in a pretty extreme way. Okay? It gets up to like 800 degrees on the surface of Venus because it's covered in carbon dioxide, mostly carbon dioxide atmosphere, covered in it. Any sun that gets through, that energy doesn't radiate back off again, just keeps heating it up. Got lots of volcanoes that spew all sorts of sulfur and other sorts of, and carbon dioxide and all that, and not a particularly nice place. I believe that we've tried to send probes down into Venus, and the Russians have tried to do this. The probes like go through the upper atmosphere, and then they basically just like disintegrate, right? So we really can't get much back from them. It's like really, really hard because Venus has just been, it's been taken over by this global warming, and it's kind of a nightmare, hellish type planet. Okay, but it is relatively similar to the Earth in a lot of other ways. Now, is this what's eventually going to happen to Earth? Maybe. You never know, but we hope it doesn't, caused by humans anyway. But this, it could, I suppose. Okay, that's Venus. Ta-da! Earth. We know a little bit about Earth. We've already studied it in some good detail. Earth, we have this idea of a habitable zone in our solar system. What that means is the area, the radius from the sun, where the orbit is, where we think life could occur on a planet. Okay? If the sun is here, Mercury's here, Venus is here, this green area just about between Earth and Mars is what we call the habitable zone. In other words, if we were closer, we might turn into Venus pretty quickly. If we were farther away from this habitable zone, well, it's just too cold, and we probably couldn't have any life. Although, when we get to Jupiter, we'll talk about the moons of Jupiter, and there could be some moons that actually have life on them. We're not sure. But basically, if you're going to have carbon-based life forms, it's good to be right about where we are. Okay? Good to be right about where we are. That's not, in some sense, that also says, hey, by the way, we kind of got lucky that we're here on Earth, which happens to be in this area. Given that there are billions and billions of stars out there, it's not unlikely that there are lots of other suns that have planets also in their own habitable zone, for what it's worth. I think if you're a Star Trek fan, they call those Class M planets, maybe? I don't know if anybody, did I say Star Wars? Star Trek? Star Trek fans. I did say Star Trek, okay. Thought I said Star Wars. Don't want to get into that battle. Anyway, Earth happens to be in this habitable zone. Mars also happens to be in the habitable zone. Okay, so let's talk about Mars. Weird font change again. Mars, the fourth planet from the sun, potentially someplace where we could send humans. We could terraform the planet and generate an atmosphere. We could maybe enclose things in an atmosphere. We might be able to live on Mars given the right conditions. Okay, you can't right now, but we might be able to live on Mars at some point. Okay, Mars right now is a very thin atmosphere. 95% carbon dioxide, about 0.15% oxygen. There is some oxygen. Okay, the problem with that is that you get very drastic temperature changes because the atmosphere can't hold any of the heat that comes from the sun. By the way, it's about twice as far away as the Earth, so the sun is a lot smaller, doesn't get nearly as much radiation. That gets about 1/4 as much because of the inverse square law. Okay? But we are going there fairly regularly, for what it's worth, with robots. Right? Why? Because we want to see what's there. There is water on the planet. Hey, if it's in water and it's in the habitable zone, maybe there's life. So we're trying to check that out. Okay? There have been in recent times, there have been 2 different robots that we've sent there. One called Mars Exploration Rover, and its sister, another one. I forget what the name of the other one was. In about 2004, that was supposed to last, I think they said it was supposed to last anywhere from like a year or 2 to a couple years. Maybe Spirit and Opportunity were the 2 of them, yeah. Only supposed to last a fairly short amount of time. It's still going. So the engineers that designed it, good job, guys and gals, because it was pretty good. The Curiosity rover just landed this past fall on Mars, and it's like pretty intense. The exploration rovers were about yay big. They're like little toys, right? Curiosity is like the size of a Mini. I mean, it's like giant, big wheels. It's kind of big. What I think is the coolest part about this, okay, so I think it's really cool that they're driving around Mars, taking pictures and rock samples and whatever. But the way they landed these things on Mars, I think, is an amazing feat of technology. Okay, take a look at how a Mars Exploration Rover landed. This is the first one I'm going to show you. Okay, so let's hit the lights again. Okay. Mars Exploration Rover landed in about 2004, and it was as follows. Okay. I think there's sound for this one. Most of this is
SSC disconnect enable on.
35. Let guys go. Hydraulics go.
So what year was this?
2004.
It took 1 year to get
AC pressurized vehicle oxygen.
Pressurizing.
SSC hydraulic pump control on.
On.
CLCDR pad B deck flush on.
On.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, engine ignition, and liftoff of the Delta II rocket with the Mars Exploration Rover.
Program response is good.
Now, Louis can tell us all about why this does not need a rocket anymore. A little bit of rocket there, but then no more rocket.
That's all it needed, right?
By the way, notice it puts that thing out so it slows the rotation.
And we just leave all the space debris up there.
Just leave it all out there. Some of it falls back into Earth. Disintegrates in the atmosphere. Okay, 7 months later. By the way, communicating with it takes about 8 minutes to get any communication to it, and 8 minutes to get back. Because the amount of speed of light. There's a little atmosphere. It does heat up, slow down a little. Enough atmosphere for a parachute. Doesn't slow it down that
ride there.
And the ride is like, I don't think they're going to drop humans that way. It's going to be bounces for a long time.
What's the gravitational force on Mars?
Gravitational force about a third, I think, of what it is on Earth.
No, I've seen the parts it's on Mars. This is the one that's about the size of a remote control car.
No, yeah, this was about this big. Think about that big. It's got little solar panels. That's how it gets its energy. It must have been a blast to create this. It's like, I'm here. And the sun goes down. All right, I'll let you see that. Its first drive.
Next morning.
This is cool though, with the wheels. Oh. You can sign up to go to Mars, by the way. You've got to sign up. It might have just ended.
One-way ticket?
One-way ticket. Something like 30,000 people signed up. I would totally do it. I would totally do it.
How much does it cost?
Well, they would pay for it. I mean, it's part of the science, you know, it's part of NASA. Come on, are you gonna drive already? Oh, it takes like 2 days just to drive. So as I said, 8 minutes to contact it. So if you need to make any adjustments, you push the button to make the adjustment. 16 minutes later, you find out if it worked. Oh, there it goes.
So they only go a few inches at a time.
Well, yeah, I don't think they're directing it. They basically say, hey, go over to this rock a mile away. And it goes, okay, and then it figures out how to get there.
It has its own.
It's got everything.
Yeah, so that it won't like.
It doesn't really have GPS because GPS doesn't work on other planets.
Yeah.
I don't think.
But it'll go around the like large or like won't just go straight and run.
Yeah, it'll go around stuff. It's smart enough to do that. Okay, so that's enough of that one. Now, that's how we landed rovers in 2004.
So do they have the actual live footage of this stuff?
Actually, believe it or not, the one we're about to see, we do have some footage from another satellite that happened to be in the right position around when the other one was landing. So we do have some footage. It's not so great. I mean, it's amazing to see because you're like, whoa, that's actually something landing on Mars. But it's not the best footage. This one is very, very cool. This is the Curiosity rover. This is how we landed this guy. This one's about the size of a mini. They'll show the launching.
Before Curiosity can explore Mars, it's got to get there first. The last stage of the launch vehicle gives the spacecraft a final push and spins it up for our 8.5-month cruise to the Red Planet.
Eight and a half months now, because it was farther in.
10 minutes before hitting the atmosphere, the cruise stage separates and final preparations for entry begin. Hitting the atmosphere at about 13,000 miles per hour, the spacecraft begins to slow down. While slowing down, the spacecraft uses its thrusters to help steer toward the landing target. We throw off weights to rebalance the spacecraft so that it's lined up for parachute deploy. After slowing to about Mach 2, or about 1,000 miles per hour, we deploy the parachute to slow down even further. Once we're below the speed of sound, the heat shield separates and the spacecraft looks for the ground with the landing radar. Once we reach an altitude of about 1 mile, the spacecraft drops out of the back shell at about 200 miles an hour. It then fires up the landing engines to slow it down even further. Once we've descended to about 60 feet above the ground and are going only about 2 miles per hour, the rover separates from the descent stage. As the rover is lowered, the wheels deploy in preparation for landing. Once the rover is on the ground and touchdown has been detected, the descent stage cuts the rover loose. It flies away, leaving Curiosity safe on the surface of Mars.
They had to make it go. I was reading something else about it where they said that part of it, they were like, what are we going to do? We don't want the thing to let go and then land on the thing, right? So they had to somehow cut the cables and then make it go and take off. So that's why it went flying that way.
And it'll land on the other rover. What are the chances?
One of the first things Curiosity does after landing is to deploy the mast, which supports many cameras and instruments. Curiosity shoots a laser at an interesting target. This helps us quickly understand the kind and composition of that target from a distance of up to 30 feet. If the target's worth a closer look, Curiosity can drive up and inspect it with the instruments and tools at the end of its arm. The drill on the arm allows us to grab some of that rock and deliver it to the laboratory instruments inside the body of the rover. Those instruments can tell us even more about the mineral composition, getting us closer to understanding whether life could have existed on Mars. Curiosity will be exploring the red planet for at least 2 Earth years, and there's no telling what we will discover.
Pretty cool, huh? Pretty cool stuff. All right, the lights again.
So why did they send it if they already had the other ones still up there?
Good question. Why did they send it? Because they already had, even though they already had the other ones up there. Well, a number of reasons. First of all, the old one didn't do exactly what we wanted it to, or it didn't do everything we wanted it to. Number one. Number two, it's newer technology. It can take better pictures. It can do different experiments. It can do it can go farther. It's bigger, that sort of thing. And we still need a lot. We still have a lot we need to learn about Mars. You know, I was wondering that. I don't think they're that close to each other. They put them in. They put them relatively close, but like could be hundreds of miles away. I mean, it's kind of like, let's say you were to go to the middle of like the Sahara Desert or something and just drop a penny, and then go like 50 miles away and drop another penny. Well, and they're not going to ever. They're just too close, or a quarter. There you go. Yeah. So anyway, Mars, we're looking at Mars for lots of reasons. It happens to be pretty close. It's another planet. It's tough to go to Venus because things tend to melt there, and it's easier to actually look at Mars. It's in the habitable zone. We might send people there in the next 20 or 30 years. Who knows? I think it would be really cool to be the first person born on Mars. I mean, you're not an Earthling anymore. You're a Martian.
We can't go to Venus forever because of the atmosphere, but how hot it is.
Yep.
So when you talk about the sun, how do we figure out what the core temperature of the sun is if we can't even sort of Venus?
Good question. So I thought the exact same thing. The question was, how do you tell what the core of the sun is? That is a very good question, and I'm not 100% positive what the answer is. It comes down to doing observations and having a theory of what it probably looks like given our, the theories. It's probably a guesstimation in some sense. They talk about it like it's well known, so I assume there's a lot more to it. I mean, people have spent their whole career to probably like figuring out this sort of thing. But yeah, it's, in some sense, we might do it by similar methods that we use on Earth. I mean, if there's earthquake's the wrong word, sunquake? I mean, I don't know. There might be some way of measuring via sunspots or something where you can measure, how the sun is vibrating or something. I don't know exactly, but that's a very good question about how do you figure that stuff out? Good question. How do we figure out a lot of this stuff? We observe it and we take all this data, and then smart people sit down and crank through theories about it. So those were the inner planets. By the way, between the inner planets and the gas giants, you know what's there?
Space.
There's a lot of space. If you had read your chapter, you would know this. The what? Not the Kuiper Belt. That's actually much farther away. But you're close. The asteroid belt is between the gas giants and thing. There is some question about whether or not the asteroid belt it was actually a planet at one point that got destroyed by something else. So I'm not really sure about that. But the asteroid belt is not dense like you see it in some pictures. Like if you were trying to fly from Earth to Jupiter or from Mars to Jupiter, you're not going to have to like dodge asteroids, right? It's just not that dense. But there are, a number of them there, but it's not as many as you might think. Okay, so we've got these outer planets, the gas giants and the ice giants. Okay, as I said before, these two are made of like the same sort of gaseous material. They're just frozen. So far away from the sun, they just don't heat up enough. And by the way, Jupiter and to some extent Saturn actually have enough heat being produced in the core because of the pressure that it actually, they do, and then gravitational forces and so forth, that they do transmit some of that heat to the external, so it keeps them somewhat warmer. Although I think the core of Jupiter itself is frozen hydrogen, which is pretty amazing. Low density worlds. I think Saturn, if you could find a bathtub big enough for it, it would actually float in water. I'm not sure about the other ones, but Saturn in particular would float. What's that?
Big bathtub.
You'd have to have a pretty big bathtub, but yes, it would float. Remember how big these are compared to Earth. Very, very, very much bigger compared to Earth. Okay?
How many moons does Jupiter have?
Jupiter has like 30-something moons. Got lots and lots of moons. Yeah, we keep finding new ones. Well, I don't know about these days, but in like the 70s and 80s, they're like, Jupiter has 16 moons. Like, 17, 18, 20. They just kind of kept noticing them. Some of them are very small. Much bigger than Earth. Jupiter is so big that it may be responsible for keeping Earth safe from a lot of comets and other asteroids that might be headed towards Earth but just get kind of steered off course because Jupiter's there. In fact, Jupiter takes comet hits every so often. In the, I think the late 90s, it took a pretty big comet right to the side. A comet broke up but just nailed it and created explosions like bigger than Earth. Like that's how giant these explosions were. But
All other dinosaurs?
and it killed all the Jupiter dinosaurs. No, you couldn't actually stand on the planet Jupiter because it's made of gas, and so you kind of go down. You'd eventually sink down, I suppose, far enough until you got to the solid core. But until then, you can't just sit there. You can't just stand on it. So let's talk about Jupiter. The first planet beyond Mars, 11 times Earth's diameter. Pretty big. It's the giant of our solar system. It's actually more liquid than gaseous when it comes down to it. It's got lots of liquid under there, mainly because of the pressures involved. The atmospheric pressure, 1,000,000 times that of Earth. Not so easy to live there if you're trying to get down there. 1,000,000 times more pressure. The gravitational pull is about 2.5 times what it is on Earth. The acceleration due to gravity on Earth is about 10. On Jupiter, it's about 2.5, I think. Okay, it's actually, oh no, sorry. It's about 25 versus 10. Yeah, 25 versus 10. Okay, big planet. Anybody know what that is?
Big red spot.
Big red spot. You know what it is? It's actually a giant storm. Yeah, a giant storm. It's been going on for decades. I don't know how long it's going to continue, but it's, you know, who knows what's causing it. They probably have theories about that. Notice it's banded. You can see a lot of different bands in there. Okay, that's from the different compositions of the various parts. It spins around this way, and I gather the different bands are just the different gases have collected in those areas, probably more or less dense, what they are. Okay, big planet. You can see one of its little moons right there. That little guy's a moon. Jupiter has an atmosphere that's about 82% hydrogen. It's mostly hydrogen, about 17% helium. So gases that we talk about all the time. 1% methane, ammonia, other molecules, mostly gases, some in liquid form. No definite surface. You can keep going down until you hit kind of the solid core. It does have a solid core of nickel and iron. It's also got that frozen hydrogen in there. Okay, daytime and nighttime temperatures about the same. Okay, why? Because it's got a thick atmosphere, so sun doesn't really heat it up or cool it down too appreciably in that sense. It's got 4 big moons. We call those the Galilean moons. As I mentioned way back at the beginning of the class, the Galilean moons were observed first by Galileo, and he noticed them, and he noticed that they went around the planet. By the way, the first real determination of the speed of light was made through the Galilean moons. What happened was there was a scientist named Ole Romer. I think he was, I want to say he was Dutch. And what he did was he looked through his telescope at the moon of Jupiter, and he said, all right, I know how long it takes the moon to go around Jupiter. He looked at it when when Jupiter was near Earth, in other words, on the same side of the sun as Earth, and he said it took about 16 minutes for it took about 16 minutes to see the how does it work? To see the, no, not 16 minutes, sorry. He knew, here's what happened. He looked at Jupiter through the telescope. He saw the moon. He said, I know when the moon is supposed to come out from being on the other side of Jupiter. Okay, he said it, however many months go by or however many days go by, I know when it's supposed to come around the other side. Then he looked at it, and that was when it was on the, let me draw this. That was when it was on the same side. So here's the sun. Here's the Earth. Here's Jupiter way out here. Let's try to do some semblance of size. Jupiter way out there. And a moon going around Jupiter, like this. Okay, what he did was he looked at that moon and he said, I know when it's supposed to first appear after it goes around Jupiter. He knows what time that should be. Every day it was about the same time or whatever, every so many days, about the same time. He then looked at it when Jupiter was way over here, if I were to draw it, right? Well, notice the difference in distance from here all the way over to here. And he didn't look through the sun, obviously, but the sun was, maybe he looked at it when it was down here somewhere, right? Because it came all the way around. Well, the time that he measured for that moon to come around was about 16 minutes off. It didn't come up at 16 minutes. It didn't come up until 16 minutes later than it should have. Well, that 16 minutes wasn't because the moon went slow or anything. It was because the distance light had to travel to get to the Earth was much greater. Okay, so the time it took for light to get from here to here was like 16 minutes longer than it took to get from here to here. And that's what caused the difference in the time for the moon to appear. So this Ole Romer said, hey, wait a minute, that means that light actually takes time to go from point A to point B. Nobody ever thought that before. They thought it was instant. Then when he came along, he said, oh, that's the way it goes. And he measured, and he was only off by a little, I mean, he was off by some amount, but only a small amount comparatively. And then it wasn't until a number of years later that people did other experiments to actually figure out the speed much better. But that was the first way. So Jupiter plays a big part in figuring out how fast the speed of light was. OK, Galilean moons. Let's look at some of the Galilean moons. Here's the largest moons on Galileo. The largest moon in the solar system is one of them, is Ganymede. OK, it's actually larger than Mercury, but it's not considered a planet, even though it's larger, because it doesn't revolve simply around the sun. It goes around its own planet. OK, so Mercury only goes around the sun, so it's a planet. OK, so there's four total giant moons. OK, oh, I thought I had more about them. Oh, wait a minute. There we go, I do. One of the moons, one of those big giant moons, is called Europa, which actually has ice caps on it. It's like the whole top part is made of ice. Okay, how do we know it's made of ice? We actually look at the light that comes off it. Remember how we did spectroscopy and spectronomy before? We actually look at the spectrum of the light coming off the moon, and we said, hey, that looks like water. So we know that it's got ice on the outer core. Well, we think, and again, I'm not sure how we know this, but liquid water is below it. And if there's liquid water on a planet in our solar system, it might contain life. So someday we may check that out. Okay. There was a satellite that went past, or a spacecraft that went past it, took lots of pictures of it, and lots of pictures of Jupiter and some of the other moons. So.
Kind of off topic, but do you know when they honored Galileo with naming the moons after him, considering the religion?
Good question. Well, yeah, good question. So he named the moons themselves, Ganymede and some other ones. Actually, did he name them? I forget. Yeah, he named them something else after a king, of course, or whatever, or maybe it was the Pope or something. I think it was a king. When did they honor him with that? I'm not sure. It's a good question. Could look it up though. Probably be on the Wikipedia page. Yeah. Oh yeah. Well, they didn't. Well, yeah. Right. He was back when he came up with, when he noticed these things, and hey, by the way, there's these moons that go around Jupiter. People weren't too pleased with that, so I don't think they were naming him after him then. But at that point, people eventually realized, oh yeah, this guy's right. So, I don't know exactly when it was. Okay, so that's Jupiter. Saturn. So when you think of Saturn, the first thing you generally think about, the rings, right? The rings. Other planets have rings as well, but the rings, they think the rings might have been caused by a moon breaking up. So a moon that either broke up or just never formed properly, and that's what caused that cool ring. They're actually not that thick, these rings. They're like less than a kilometer thick, I think. These are pretty thin, but they happen to bounce light off them, so you can see them. Saturn's about 10 times the diameter of Earth. It's twice as far from Earth as Jupiter. Remember on the Djibouti map we saw it was another huge jump just to get to Saturn. Really, really far away. Okay, it takes a pretty long amount of time to go around the sun. This is the one that could float in your bathtub. Not very dense. Another gas giant. So I happen to be looking up something on Saturn and notice there's actually news on Saturn this last week. Okay, one of the big things in news is that we noticed this. By the way, we have the Cassini spacecraft is actually orbiting around Saturn right now. So we've sent a spacecraft to Saturn, and it's orbiting around Saturn. Pretty cool. It is taking lots of pictures of Saturn and one of Saturn's big moons. And the thing right now happens to be taking pictures of this giant hurricane that's like 10 times bigger than any hurricane ever on Earth. And they're not exactly sure what's causing it or how long it's going to last or whatever, but I mean, in the news. So we're still learning stuff about these planets every day, especially the ones we have satellites around. So as I said, the rings were possibly bits of moon that never formed, okay? Torn apart by these tidal forces, which we mentioned last week when we talked about the tides. When a moon is closer or farther away, there's these tidal forces that pull it. inner part of the rings actually travels faster than the outer part. So it's not one big ring that's kind of going around. It's like little individual bits and pieces going different speeds around it. They're not going different ways. They're going the same way, but they're just going different speeds as they go around.
I thought they named the 4 different sets of rings.
Did they name the rings? They probably did. I'm not sure. I did not hear about that. Not heard about naming the rings. And each individual rock as part of the ring is independent. So it's just a bunch of rocks that are independently going around. Pretty cool stuff. I don't know what they. I don't know if that satellite. I haven't seen too many pictures of it, but I think Cassini's taken some pictures of it. This Cassini satellite actually had a little baby satellite of its own, or a lander, I should say, that actually sent a lander onto Saturn's moon Titan. So if someone ever says, "Hey, the only place we've ever landed landers is the moon and Mars," you can say, "Aha, Saturn, right? The 1, 2, 3, 4, 5, 6th farthest planet from Earth. We've actually we put a lander on one of its moons." The moon Titan, Titan being big, it's one of the large moons of Saturn, and we landed it there. And it's pretty rocky. Looks a bit like, I don't know, Saturn. I mean, sorry, a little bit like Mars or the Earth, the rocky parts of Earth. I'm not sure what else came out of it, but called Huygens, the name of the satellite or the name of the lander. I think that's pretty cool that we sent a satellite to Saturn and then had a lander that we put on it, that we put on one of its moons. That is pretty cool stuff.
Was it the same, like the vessel that delivers the satellite to orbit?
Yeah, everything was there. It was all together.
Package deal?
One package deal. Cassini went out, and then Cassini sent the little lander, and the lander landed and took a bunch of pictures. Pretty cool.
How long did that take?
Good question. It took a number of years to get there. I don't remember how many, but it took a number of years to get there. We could look that one up. It's another one to look up. But the beauty of this chapter is everything is so cool about it, and you can look up all this stuff on, NASA's got giant websites about all these things, and Wikipedia's got lots of information, so pretty cool stuff. Okay, next planet, Uranus. Despite how you might want to pronounce it, that's how I'm going to pronounce it and how astronomers pronounce it. Twice as far from Earth as Saturn, so it's another jump, as we saw on the map earlier. Okay, the diameter 4 times that of Earth. Okay, it's huge, another huge planet, not as big as the other two, but big. Weird planet. 98-degree tip. If this was Earth going around its orbit, this is the way Uranus is tipped. Why is it tipped like this? Who knows? We think it was because some giant thing hit it at one point and knocked it over. Boop, knocked it over. So, yeah. So it's spinning like this. Yeah. Let me think. This isn't the one that's spinning the wrong way. I think Venus might be one spinning the opposite way of all the others. I think so. One of them does. I forget which one. Uranus also has a ring system like Saturn. It's got a methane atmosphere. You would not want to try to breathe in that atmosphere. And it's extremely cold. Why is it so cold? It's so far away from the sun. I mean, the sun looks teeny tiny from Uranus. Very small. Okay. Then we get to Neptune. Neptune, past Uranus, another long way out. Again, 4 times the diameter of Earth, a little bit smaller than Uranus. Mainly hydrogen and helium, kind of like Jupiter. Okay. Highly elongated elliptical path. In other words, if this is the sun, the path of Neptune looks like this. Now I've made it much more elliptical than it really is, but very elliptical. Okay. I think this Pluto actually crosses it somewhere in here. I think. So kind of Pluto looks like that. But Neptune's just a very elliptical orbit when it comes down to it. Okay. Neptune. This is something cool about physics. And I might have mentioned it when we talked physics a while ago. Neptune was actually predicted mathematically where it was. We didn't find it. Nobody saw it in a telescope until somebody said, "Hey, you notice how Uranus actually wobbles a little in its orbit? It's not the right orbit for the other planets that we have. It just doesn't quite fit. It should be a little bit more elliptical or less elliptical or whatever." So somebody sat down, and this was before we even had calculators and things, so they had to do all this with like slide rules and pencil and paper. And they did all these calculations, and they said, point your telescopes over this way, there's probably another planet there. A couple months later, hey, another planet, Neptune. Okay, pretty cool. That's how, like, you know that, like, gravity works, right? Because they did all this using just the theory of universal gravitation. So Newton would have been proud. I think Newton would have been very proud. They should have named it Newton. Now you already had a unit. So anyway, notice faint rings as well. Okay.
What's the rings made of? Same?
I don't know what the rings are made of. They're probably rocky, I imagine, because it's probably the same sort of thing.Maybe a moon that got pulled apart by tidal forces, something else. Yeah. And then finally, even though it's not a planet, we can still talk about Pluto. Classified as a dwarf planet. Okay, these planets that aren't big enough to become real planets. Again, the reason is because there's lots of them out there. We're not going to name them all planets. Pluto just fell off the, planet list. And it's all, by the way, it's not very much like, especially it's not very much like the giant planets. It is kind of rocky, very elliptical orbit, kind of like comets. And most of the time, it is beyond Neptune in this thing called the Kuiper belt, which we'll talk about in a little bit. And so it's very much like a lot of the other things out there. So another reason why it probably shouldn't be a planet. Okay? Former planetary status is more historical than anything else. We saw it with a telescope, said, oh, it looks like a planet. It's actually got another little moon around it. It's almost as big, so really it's kind of like another planet, that sort of thing. OK, so Pluto. All right. Those are all the planets and some of the moons. Let's talk for a few minutes about Earth's moon. Okay? We know a lot about the moon. Why? Because we've sent people there. Right? We actually have been there lots of times. We've sent people there, sent probes there, sent satellites there. It's pretty close to us, relatively speaking. Okay? Diameter, about a quarter of that of Earth. If we were to come to this solar system from another solar system, we would probably say that there's two planets here, a double planet system. We'd probably say that, hey, look at that double planet over there. We wouldn't just say, hey, that's Earth and some moon, because moon is so big relative to the size of Earth. No atmosphere, no weather, lots of craters and stuff because there's no weather to erode it away. Okay, pretty cool. 12 people actually stood on the moon. This one happened to be Buzz Aldrin. Now, for all of you naysayers who think we never went there, you're wrong. We actually, what's that? People say that there's a big conspiracy theory about going to the moon, and it was filmed in a set somewhere. We wanted to show up the Russians. Lots of reasons why we know this not to be true. Number one, we left stuff up there that we bounce light off every so often to check how far away the moon is, and the light actually comes back to us, so pretty good indicator. Okay. Second thing, so we had lots of radio broadcasts from the moon. If the Russians really wanted to say, hey, you guys didn't do this, they were listening to the same radio broadcasts, and nobody said, hey, these radio broadcasts are coming from Houston, Texas, or from somewhere else, right? They knew they were coming from the moon. Okay. We have moon rocks that they brought back. In fact, there's a really good story about some moon rocks that were lost for a number of years. We just lost them. Oops. They're like the most valuable thing on Earth now, and we lost them. They did find them eventually. Some guy stole them, I think. Some intern stole them, I think. The flag, when they planted the flag, it did not wave because there was a breeze. It waved because there's no atmosphere, number one. Number two, it was held up there with a little post, and it just flapped around when he went, flapped around like anything would, with no atmosphere. Anyway, that's the moon. Okay, how'd the moon form? We talked about this the other day. The moon probably formed, this is the way we think these days, some other giant object smacked into Earth, made Earth into this molten planet for a while, and it ripped off enough mass to form the moon. And by the way, the moon was not very far away, relatively speaking. Instead of 300,000 miles, it started out like 30,000 miles away. It would have been giant in the sky. Would have looked really cool. Tides would have been immense, and you wouldn't have been able to live anywhere near the ocean because you would have been swept away every day. And the planet was on fire at that point too. But yeah. So that's it. The moon phases. We all know a little bit about the phases, but keep in mind when you're looking at the moon, the whole moon is still there, right? You can't see through the crescent or whatever. Okay, and we've got all these moons. When we're in full moon. That's because the sun is way on the other side and you see the whole moon. Okay? Full moon is when you get eclipses that make the moon disappear, because the Earth comes between the sun and the moon. New moons, when you can't really see the moon because the sun is on the other side of it, is when you get eclipses of the sun. Okay? The moon also spins on its axis, and we learned, I think we learned the other day also why the moon is always facing one direction. It's because it's tidally locked. Because over time it's slowed down because of the tidal forces from the Earth. Okay? Eclipses. Eclipses are pretty cool. When the moon is between the sun and the Earth, this is when you can start looking at the sun. By the way, the fact that the moon is the same size roughly as the sun when you have an eclipse just happens to be because of the time we live in. Like a million years ago, the moon was much bigger and covered more of the sun. And 10 million years from now, it's going to be much smaller, and you won't be able to look at it during an eclipse. There will no longer be complete eclipses. Kind of cool. Anyway, that's called a solar eclipse because the sun is being blocked out. Well, if the Earth is between the moon and the sun, we get a lunar eclipse because the moon is actually now eclipsed. It's actually a cool picture in your book about how red the moon becomes because it still gets some radiation, but it comes nice and red when you see a full eclipse. It doesn't completely go away. It's really cool. And that happens much more often. So you can definitely see eclipses. I don't know when the next one's going to happen, but you should see it. What kind of eclipse do we get when the sun is between the Earth and the moon? What's that, Louis? Of course it doesn't happen. I mean, the moon will be over here. That doesn't make sense. The moon goes around the Earth and stays around the Earth wherever, right? Yeah.
Are you going to be here in November?
Sorry?
Are you going to be here in November?
I will not be here in November, hopefully. I better not be. Why? Is that when it's going to happen?
Here in Africa.
Oh, yeah? A full eclipse?
November 3rd,
Oh.
2030.
Well, you know what? I'd rather be home than see that. I've seen it before.
2017.
August 21st, 2017 is the next one in the US? Huh. It's a while from now. Oh, well. Andy, you said what? Why the moon phases happen?
No, there's that the face on the moon.
Oh, the face on the moon.
Have they ever explained that?
Well, I think it's just a bunch of a bunch of like asteroid hits and meteor hits and all that. So yeah. Yeah. Oh, here we go. I forgot to put this in here. That's what the moon looks like during a full eclipse. Okay. You get some refraction of light around the Earth that actually does hit the moon, and you can see it. So it's a beautiful color. Okay. Asteroids. Asteroids are small bodies, rocky bodies that orbit the sun. They're not big enough to be planets. Most of them are potato-shaped, right? They're kind of oblong, potato-shaped. Mars has 2 moons, by the way, that look kind of like this. There's probably asteroids that were captured. Okay. You can't see asteroids from the Earth. Okay. You can see them when they're on the ice, that's how people find these like asteroids that have hit the Earth, right? Because they show up on the ice a little bit better.
So you mean like in the polar ice caps?
Yeah, like in Antarctica, you can find asteroids that have hit the Earth easier because it's easier to see them. Yeah. Comets, on the other hand, anybody ever seen a comet? I was actually on the USS Cleveland in 2007, I think. No, 2007. And I watched Hale-Bopp Comet, which is this one. I'm not sure. I forget if it's this one. I think that might be the one. In the middle of the ocean with the lights dark on the ship, it was amazing. Amazing. And then I got to use night vision goggles, even more amazing. It was the coolest thing I've ever seen. Comets are actually somewhat different. They have a lot of water in them. Okay? Water, methane, ice, they're like dirty snowballs flying through space. Okay? Most of them are in these 2 places called the Kuiper Belt and the Oort cloud, which we'll talk about in a minute. Very elliptical orbits. Anybody ever heard of Halley's Comet? About every 76 years it comes back. There was once it came by in the 80s. I saw it. You were in grade school? Yeah, me too. I was in grade school then too. It was pretty cool. I didn't actually put my eyes on it, but it's out there, and it's going to come back when we're in our 80s. So, you know. Hopefully I'll be around then, cross my fingers. The tails of comets are swept out by the solar wind. Okay, and I think I have a picture of this. You can see the tail is always facing away from the sun in a comet. Okay? I'm not going to take the time now to read this, but in your book, read that little diagram. It's kind of cool. Okay? On Earth, sometimes we get struck by some of these non-planet items. If we have an asteroid that has bits and pieces that come off it, it's called a meteoroid. Okay, I'm not going to ask you to memorize these terms. But most meteoroids are like sand size. They're very, very small. Okay? Once the meteoroid hits the Earth's atmosphere, okay, that's when you get a shooting star or a falling star. Because what happens is it's going really fast, like 50,000 miles an hour, and it hits the atmosphere, and it's tiny, but it goes down through the atmosphere, heats up so much, glows, and then burns out. And that's what you get when you get shooting stars. Okay? Those are meteors.
So it's technically not a star.
Oh, it's not a star at all, no. That would be bad news. If a star actually came close enough to Earth, we would probably be destroyed. But so it's not a star, no. A meteorite is what happens when a meteoroid that becomes a meteor hits the Earth. It goes all the way through the atmosphere, is big enough to not burn up completely, and strikes the Earth. This happened in Russia about a month or so ago, and you might have seen pictures about it. It was crazy. Giant, like, sonic boom. People took pictures of it. Russians have a lot of dash cams in their cars, so they got lots of pictures of this thing. Did it hurt anybody? I forget.
There were a lot of windows that were shattered.
Windows shattered, yeah. I don't know if anybody got hurt. Yeah. But so beyond Neptune, there's two things out there. There's the Kuiper Belt, which is where we have lots of these little asteroid-like planetoids and things. Pluto's out there. Okay? Lots of rock-covered planetoids. Responsible for many comets. What happens is there's lots of comets out there, and when they, on their elliptical orbit, when they come nearer to the sun, that's when you get this cool comet that goes past the sun. Farther out, the Oort cloud. We didn't actually discover this till a few years ago, really, like 10 or 20 years ago. Outside that area, there's a huge amount of space that's filled with these little, not filled, every so often there's these little comets and things. Also produces lots of comets. Some of the comets whip by the sun, and then you don't see them again for like 1,000,000 years, right? Because they're like way, way, way out there, and then they come back and whatever. So you get some comets from these two things. We don't really know that much about these things. It's tough to see anything out there, but we can do it. Now, question. Where is the furthest spacecraft we've ever sent out right now? Just left the solar system, depending on what your definition of solar system is. It's probably in the Oort cloud or in the Kuiper Belt still, called Voyager 2, I think, which overtook Voyager 1, I think. Just going out there, going away. It's got a cool gold record on it, which has all sorts of cool stuff about Earth that Carl Sagan put on it, and his wife put this together. It's got like pictures of people, and it's all inscribed in this gold disc. And it's got formulas and things on there, and it's a mathematical description of pi and accounting and all that. It's cool. It's just in case anybody ever happens to find it. Well, it's like tells you how to count. Kind of cool. All right, take a break. We'll get back and do stars and galaxies. 10 minutes, please. 10 minutes. Okay. All right. Second to last chapter. Woohoo! This is on stars and galaxies. Okay. We already talked a little bit about the sun as a star, but remember, our star is one of billions of stars in our galaxy. And then we'll talk about the billions of galaxies that there are. And we'll talk about clusters and blah, 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 blah. We'll get to a lot of cool stuff here. This, again, is one of those ones that it kind of blows your mind about the size. Okay, we look up into the sky. Okay, what do we see? We see constellations. Right? We see lots of stars just with our naked eye. We see lots of constellations. The constellations are named for the shape that they're in, generally. And you can have a lot of fun peering up at the sky and picking out constellations. If you get a good constellation map, you can look up and you can see. And one of my favorites is Orion. one that looks like the guy with the sword or whatever, and you got his belt and whatever, right? There's also Ursa Major, which happens to have the Big Dipper in it, right? And using the Big Dipper, you can find like the Little Dipper, and then using that, you can find the North Star, and then you can figure out which direction north is. And stars are used for navigation sometimes. The SR-71 used stars for navigation. Had a cool little observatory in the top of it. The co-pilot would have to look up, and or the navigator rather, would have to look up and check where the stars are and to navigate. It was pretty cool stuff. What's interesting about constellations, and some people don't really notice this. Well, I guess that's next. Let me go to the next slide first to show you. This is it. Nope. This is it. Constellations, the stars in constellations are not in a nice line away from us, right? Some are like much, much, much farther away than others. In the Big Dipper, this star is 93 light years away. Light year? I don't know if we even mentioned this yet. Is the distance light travels in a year in outer space. 300,000 kilometers per second. It's trillions of miles per year. Okay? That's how far it is. Now, the sun happens to be 8 light seconds away from us. No, sorry, 8 light minutes away from us. Okay, meaning the sun to us, 8 light minutes. Takes light 8 minutes to get here. If the sun somehow extinguished itself right now, we wouldn't know about it for 8 minutes. Right? We'd be perfect. Nobody would be able to figure anything. Like, there's no way to know about it until the light stops getting to us, I guess. But anyway, the next one, 69 light years away. This star, 360 light years away. That's how far away this one is versus this one. So even though we look up at the stars and we see them in this nice kind of planar view, one might be here, and then one's here, and then one's here, and then one is way back here, and it's just they're all so far away that we really can't you can't differentiate them with your naked eye. Constellations, as the Earth goes around the sun, whatever you're looking at is a different constellation picture. So in like November, you're looking at this set of pictures, which is that direction in space, right? You come around to July, and you're looking the opposite direction in space. And that's why we get different constellations during the year. Now, at night, as the Earth turns, you get a different picture of constellations as well. But you won't see the same, like if you look outwards, you won't see the same thing, the thing for another 6 months. Unless there happens to be a solar eclipse, in which case, if you're over here and the sun is dark because of the moon, you will see this picture of the stars. That's kind of cool, right? So that's an interesting way to think about it. But at daytime, you can't see. Now, during daytime, we do point telescopes at various parts of the world, various parts of the sky that are radio and X-ray and gamma ray getting. So we do see different parts of the sky at any given time. But if you're just looking at night, you'll see a totally different picture. Okay? In the northern hemisphere, we can always see the North Star. Yeah, you can always see it. Because it's actually pretty much directly above the way there spins. And then as we go around the sun, it basically stays in roughly the same spot. Yeah. This is what the Big Dipper looks like at various times during in the northern hemisphere during the year. Sometimes it's facing up, sometimes it's sideways, sometimes it's upside down.
It's always true that
and by the way, the North Star, I guess is it the Big Dipper that points to the North Star? I guess it is, that way. Yeah. Sorry, is it true what?
Is it always true that, like the Little Dipper always pours into the Big Dipper, or the Big Dipper pours into the
It is true, one or the other, I think. One pours into the other. I'm not sure which one it is, but yeah. I once taught an astronomy class, and we had a star chart of all the constellations, and it was this big, giant chart. It had like 100 or 200 constellations on it, maybe even more. It had a ton of them on there. And I told the class I'd give somebody an A if they were able to name all of them. And one kid, really, whoa, cool. Next thing you know, like a week later, he's like, I can do it. So he did it all for me, and he drew them all out on this blank chart. He drew all 100 of them, or whatever it was, and I gave him his A. So, no, I'm not doing that for you guys. Some of you guys will waste all your time doing that.
Yeah.
Okay.
You have jobs though.
Stars are not all one color. Now, in an earlier class I said that the sun is white. If you look at it, predominantly it is white, although it does have a yellowish glow to it because there's actually more light of a yellow nature coming from the sun. Okay? Different stars have different colors. This is a picture, I'm not sure what telescope took this picture, but it's pretty cool, looking at all the different colors of all the stars. Now, at night, our eyes have a tough time differentiating colors. That's why they all pretty much look white. But if you have binoculars, wherever, you can see a shade to some various stars, just like you can see that Mars is relatively red when you look at it. The color, the temperature is dependent on the color. The color is dependent on the temperature, the predominant temperature of the star. Okay? For instance, a red star, being a lower frequency of light, is actually a cooler star than a blue star, which is a higher frequency of light. Okay? Blue star is actually twice as hot as a red star because it's got about twice as much of temperature. Okay? Or twice as much frequency, rather. Okay? So it's kind of cool. We can measure the brightness in a couple different ways. We just look at it and say, how bright does it look? Right? It's not, this is different than the color. We just look at it and we say, hey, how bright is that? And we measure it against another something, another brightness indicator. Okay? We also can measure it by the intrinsic brightness. Now, how we measure that is, I'm not exactly sure, but we measure it saying the star is this such and such a size, and it's such and such a distance from us. Therefore, it's going to have a certain brightness based on that. It's not just how it looks. It's how it is in real life if you were like such and such distance from it. That's how we measure the actual brightness. Okay? We have a standard brightness, which we call the brightness of the sun, luminosity of the sun. And we measure all the other ones against luminosity of the sun. Why? It's just like, why do we measure the distance to Earth from the sun as one unit? Well, just because we know the sun. Okay? Okay, here's a check question. If we measure the sun's luminosity as L sub sun, if we were twice as far away, what would the apparent brightness be? The same, half as much, 1/4 as much, or 4 times as much?
Half as much.
So it's same quarter.
Oh yeah, 1/4.
Only one person remembered what we talked about.
Inverse law.
The inverse square law. Look, the inverse square law. Thank you very much. A for you. Alan gets an A. I heard it here first. So it's 1/4 as much. Why? Because it's twice as far away, and we got 1/4 of the brightness, inverse square.
Question.
Yeah, question.
How do they tell the difference between, like, for example, the sun generates light, right?
Yes.
Whereas the moon reflects light. So how are they able to tell the difference?
How do they tell the difference between the moon and the sun in terms of?
Like, for example, Mars seems red because it reflects light.
Oh yeah, and it's a very iron-rich surface and so forth, is why the Mars is that way. How do they tell the color or the brightness or what?
Well, no, like stars generate their own light.
Oh, stars do generate their own light. Remember at the beginning of class I said it's really hard to see other planets? It's because they don't generate their own light. I think telescopes have gotten to a point where we can barely see other planets. Mainly, the reason we used to be able to tell there were planets is because we noticed that there were, how did we do it? It had to do with the fact that you could notice the sun itself wiggling a little in its orbit. You said, oh, there must be a planet there. But yeah, now we can kind of barely see some planets way far away. But yeah, they are nowhere near as bright. So you totally know if they're farther away, they're not. Now, the ancients did think that our planets in our solar system were stars. They called them the wandering stars. That's how planet actually means, I think, is wandering star. Why? When you look up at the sky, during the night, the stars will all go in one big thing. During the night, the planets will wander through the stars a little bit because of the fact that they're in a different orbit around the sun. The stars are so far away that they're not affected by the orbit of the sun. So that's why they call them that. So think about, you're an ancient person, you don't know anything about the science or anything, and you look up and you see all these stars, and everything goes one direction, and there's 5 stars that go, or whatever. Oh, that's pretty cool, right? So you call those something different. That's what they had special significance. Now, the Hertzsprung-Russell diagram. This is the periodic table for astronomers. Okay? It's like the periodic table for chemistry. And what it does is it shows us the types of stars in the galaxy or the universe and where they lie based on the temperature and the luminosity. Okay? So, and this is an absolute luminosity. If you look, some stars are very, very hot, yet not that bright. Other stars are very cool, but extremely bright. Some stars are bigger than other ones too. Okay? These stars up here, these red giants, happen to be very hot and very bright. Stars way down here are called white dwarfs and happen to be very small, very cool and not very bright. Look where most of the stars are. This is called the main sequence. Most stars spend most of their time somewhere along here. In other words, if they're about 10,000 degrees, they're about a luminosity of 1, which is roughly what our sun is. Okay? Roughly what our sun is. Okay? I'm sorry, I got this backwards. I did get this backwards. Hotter and smaller, or hotter and more bright is over here. Cooler and, cooler is this way. Brightness is this way. So cooler stars, but kind of less bright. I said that wrong again. Hotter stars, less bright, are over here. So white dwarfs, very hot, not so bright. Kind of like I feel right now, not so bright. Hotter and very bright way up here. So red giants, not so hot, but very bright. Okay? The sun, a little over 6,000 degrees. Okay? Brightness of 1 for our sun. Is there anything particularly special about our sun? It's in the main sequence, not so special. Okay? So, if you think, is our sun unique? Well, it's unique to a certain extent, but because it's ours. But otherwise, it's not so different. Okay, so HR diagram, check question. Sun is a pretty average star, actually. Okay, nothing too unique about our sun. Pretty average. Okay, we said right at the beginning, nebulas, or did we use another term? I forget. Nebulas is where stars start. Basically, after like the Big Bang, other stars produce other stars by exploding and creating other nebulas that new stars are created from. Okay? We already said this. Stars become a protostar, and then once fusion starts, in other words, once it ignites, then it becomes an actual star. Okay? Some stars, like our sun, we have predicted anyway, will become a red giant. What happens is, if you look at the HR diagram here, what's going to happen to our sun is it's going to go from here up to here, and then actually back over to here, and then eventually down to here. That's what's going to happen. It's going to still spend most of its time in the main sequence, but some of the time it's going to be this red giant. Other times it's going to be way over here, and then it's going to finally lose most of its mass and then end up as a kind of a burnt out white dwarf star.
So now, when those kinds of things happen, will it retain its gravitational pull?
Good question. So why does the sun actually become much smaller? Well, because it's lost a lot of mass.
Running out.
Okay, and it's running out of mass because that mass is turned into energy from the nuclear fusion, right? So once it eventually becomes a white dwarf, and by the way, I have a picture a little later that shows a white dwarf, most of it has become carbon, actually. Once it's carbon, it doesn't fuse so well. It can fuse all the way up to lead, but most of it's going to end up as carbon. And what do we know about really, really dense carbon?
Lithium?
Nope.
Helium?
Nope.
Something with
I'm pointing at you because you work in the industry. Or you used to.
What was that?
Wow, that's such a beautiful ring. Diamonds. White dwarfs can actually be made of diamond. In the core, anyway. Yeah. Oh, here's right here. Ta-da! A white dwarf. A white dwarf cools for eons. Eon is a long time, right? Cools for eons until it's actually too cool to keep emitting light and eventually just burns out, okay? Because it's not fusing anymore. If it's part of a binary system, in other words, two stars that are near each other, it can actually suck energy from the other star, or suck matter from the other star, and then eventually it can explode into a nova. But this is kind of a cool picture. And the inner part of this is a diamond. It's not like a trillion carat diamond. Right? Yeah.
Definitely not De Beers.
Definitely not De Beers, right. Okay, so stars, when they finally collapse, if they're not going to become a white dwarf, what happens is they end up in this really cool thing called a supernova. What happens is they keep burning, and they're relatively small until they finally burn out. And when they stop burning out, all the pressure, the outward pressure that's caused by this nuclear reaction disappears. In a matter of hours, gravity says, I win, takes over, crushes it. The crushing is such a huge reaction that it ends up exploding. And supernovas can become brighter than the entire rest of the galaxy in their explosion. The coolest part about this is, in that explosion, in that crushing, that's when the heavier elements like gold and iron and uranium and all those elements that we find on Earth are created. So, and in fact, a lot of the other ones too, that like the ones that don't normally get created in a regular fusion reaction, carbons and things that aren't normally created, things that you're made of, created during a supernova. Okay, so way back when we started Earth science, I think it was Earth science, where we talked about the fact that we're all star stuff, we're all supernova stuff, is what it really comes down to. Supernova explodes, creates all these cool elements, they end up becoming planets, and that's when you and I become around. So let me show you a couple of little videos on supernovas, because I can't do it justice. Let's see. What is a supernova? We'll start with that one. Okay. All right. Yeah, Eric, want to hit the lights there? Thank you. Okay. Okay. Let's see. Is this the one? Yeah. So I'm not sure this reporter actually knows anything about supernovas. She's kind of cute, but what? No, she's very attractive. But she talks like she's reading off cue cards sometimes. But she says a lot of cool stuff about supernovas. So pay attention.
Hi, I'm Emerald Robinson. In this What Is video, we're going to take a closer look at supernovas. A supernova is a massive explosion generated by a dying star. A star in our galaxy goes supernova approximately once every 100 years. The explosion hurls matter into space and can shine as brightly as an entire galaxy for short periods. Stars are giant nuclear reactors, producing energy by fusing hydrogen into helium. Eventually, however, stars run out of hydrogen to fuse. When this occurs, the star fuses helium into heavier elements, including iron. The star's core shrinks while its outer layers expand, creating a red giant that consumes surrounding planets. What happens when the sun runs out of helium? Fusion simply ends in small stars like our sun. The star becomes a white dwarf and slowly fades away. When a large star depletes its helium reserve, the core collapses within seconds, causing temperatures in excess of 100 billion degrees. The outer layers of the star collapse as well, only to explode outwards in a massive explosion known as a supernova. Supernovas generate enough energy to fuse elements heavier than iron. Gold, silver, uranium, and other elements with high atomic numbers are created in supernovas. What's left of the star's core becomes a dense neutron star or forms a black hole, an area of such densely packed matter that not even light escapes its gravitational pull. After a supernova, material expelled in the explosion may form nebulae, massive interstellar clouds of gas and dust. Over millions of years, gravity pulls nebulae material together into a dense hot core called a protostar. Protostars eventually become newborn stars. The new star's gravitation affects surrounding nebula material, which may form comets, asteroids, and new planets. It's truly the solar circle of life.
Yeah, so
For thousands of how-to and
what's that? All right, where'd it go?
So the supernova were to explode like shooting close to a planet, you can't possibly just take it out.
If a supernova explodes anywhere near anything, it takes out the entire area.
Solar system?
So, yeah, I mean, a solar system is obliterated. In fact, like a good portion of the, like that neck of the galaxy is destroyed. Like supernovas are like big, big deals, right? And like I said, they can be brighter than the rest of the galaxy combined. That's how like immense they are. She said every 100 years. I think the next video would say supernova happens in our galaxy about every 50 years, something like that. Oh. Let's look at this one. This one's a little more, also narrated by a woman, but you don't see her, and she's a little more scientifically, like, sounds a little more. This is actually taken from the Chandra Observatory X-ray.
We have booster ignition and liftoff,
which is an X-ray telescope that's actually in orbit around Earth.
Columbia reaching new heights for women X-ray astronomy.
The main thing that Chandra does is take these superb, sharp images.
Nothing as beautiful as Chandra sailing off on its way to work.
A supernova is the explosive death of a star. As one of the most energetic events in the universe, a supernova may temporarily outshine the rest of the galaxy in which it resides. But what are supernovas? Every 50 years or so, a massive star in our galaxy blows itself apart in what astronomers call a supernova. Supernovas are some of the most violent events in the universe. The force of the explosion generates an intense flash of radiation, as well as shock waves analogous to sonic booms. These supernovae are often best seen through X-ray telescopes like Chandra. Dr. Patrick Slane of the Chandra X-ray Center talks about supernovas in our own galaxy.
In our own galaxy, these types of supernova explosions occur every 50 years or so. The explosions pound the nuclei of atoms together so violently that they build up all the heavier elements of the periodic table. These are flung out into space where eventually they mix with other interstellar gas and form new stars and planetary systems enriched with these heavy elements. Although our galaxy seems to be in somewhat of a drought for supernova explosions, with the last one being observed in 1604, we see the remnants of these explosions all over the place. The outgoing blast wave from the explosion sweeps up the interstellar gas and heats it to temperatures so high that they glow in X-rays. They can be 40 or 50 light years across, and for the youngest ones, we can actually still see them expanding.
Pat Slane explains how one kind of supernova, called Type 1A, works.
Many stars are formed in binary systems. After one star in the system evolves into a white dwarf, it's possible for the companion star to approach the end of its life, in which the hot interior causes the outer layers to expand. If they expand enough, some of the gas can fall over onto the white dwarf. This transfer of matter onto the dense white dwarf can eventually increase its central temperature enough to detonate the entire compact star in what's called a Type 1A supernova explosion. Here, the entire white dwarf star is obliterated. This type of supernova always produces about the same brightness, unlike supernova explosions of massive stars, which can vary a lot depending upon the mass of the star. These Type 1A explosions can be seen in other galaxies out to incredible distances. In fact, they provided the first evidence that the most distant objects are moving away from us more rapidly than expected, the result of dark energy accelerating the expansion of the universe.
X-ray telescopes, particularly Chandra, are very important tools for astronomers to study supernovas. The supernova explosion is incredibly energetic and can heat any gas that surrounds it to millions of degrees. The debris field and high-energy particles within it are what astronomers refer to as a supernova remnant. Such remnants are known to produce intense X-ray radiation that can last for thousands of years. Pat Slane explains how Chandra's images are used to analyze the debris field and reconstruct the star's explosion.
Because the gas in supernova remnants is so hot, it radiates in X-rays. By measuring the spectrum of the X-rays, that is, the energies of the different X-rays that come from the remnant, we can tell how hot the gas is and what it's composed of. This lets us identify the heavy elements that were produced in the star and its explosion, and compare these with our theoretical models of how these explosions occur.
Scientists think that supernovas can trigger star formation and probably led to the formation of our very own solar system some 5 billion years ago. This supernova also likely seeded the cloud with elements like carbon, nitrogen, and oxygen that eventually went into the sun, planets, and ultimately us. These elements are manufactured deep in the interior of massive stars and would, for the most part, remain there if not for the cataclysmic supernova explosions. For these reasons that are very close to home, and to others ranging to the quest to understand the history of the universe, Chandra will continue to study these fascinating objects we call supernovas.
Pretty cool, huh?
For more information about the Chandra X-ray Observatory, visit our website at chandra.harvard.edu.
There you go. So, yeah, you can hit the lights now. It's pretty cool stuff. Yeah, supernovas are pretty cool. And that's where we're all from. Okay. All right, so those are supernovas. Then we get into black holes. Okay, black holes are, obviously, they're brought up in science fiction all the time, and we talk about them kind of in this, like, whoa, black holes. Well, they are kind of interesting, and we don't know that much about them. But what happens with a black hole is when you get a supergiant star that has enough mass to just keep shrinking and keep shrinking and keep shrinking because of gravity, eventually it will collapse into itself so much that it becomes infinitely dense. Right? It just keeps collapsing into a point that big, which is all the mass in that huge giant star. Okay? It has so much mass in such a small amount of space. There's an area around it where not even light can escape. Okay? And that's why it's called a black hole. And what do you mean not only light? Light is somehow affected by gravity? Light is affected by gravity. Light actually bends when it goes around big, huge objects like stars and things. Not that much, but enough so that we can see it. In fact, that's how we see some of the farthest things in our galaxy is using gravitational lensing, meaning we kind of can look at something and then see stars around it from farther away because they've been magnified by gravitation of other like galaxies and things. Okay, black holes are not some sort of magical sucking machine like you might have heard of, right? They're just like gravity they're just a mass in a much, much smaller area and much, much, much more dense than anything else in the universe. Okay? If you look at, let's say you were an indestructible person standing on a star, somehow indestructible, right? If the star shrinks, right, and it's half of the radius, well, you get 4 times as much of your weight. So if here you weighed 10,000 newtons, and it was half much radius, you'd have 40,000 newtons. It's only because you're closer now to the center. That's all that's about. If you had stayed out here, you'd still be 10,000 newtons, because you're still the same distance from the same amount of mass. The law of gravitation does not change because the star is shrinking. It's just where you are in relation to the center. What that does mean is as you get closer, you get heavier and heavier to the surface of whatever that is. When you get a black hole, which is a point, well, you come to a certain amount of distance, well, nothing can escape. You get to remember when we talked about the escape velocity on Earth, like how fast you had to shoot out a rocket in order to escape Earth's velocity, Earth's gravity? Well, I forget what it was on Earth. It wasn't it was 12 or 15 kilometers per second or something like that. If it's above 300,000 kilometers per second, light can't even go that fast. So light gets drawn back into the black hole. In your book, there's a great description of what would happen if you tried to like fly a spacecraft into a black hole. There's actually a point where there's this edge. What is it called? It says it in the book. Sorry? The event horizon. Well, there's two. There's like the photo horizon or something and the event horizon. One where if you go just below it, you can still get light out of there. Once you go too far below, the light actually tries to go out and then curves around, and you can't get any more light out. So it's pretty cool stuff. The book has a really good description about that. It also talks about how if you get close enough to the black hole, because the light can't escape and because the light coming in is affected so much by the gravitational pull, if you were able to survive, you could watch the entire rest of the universe get destroyed before you would die. Your time slows down enough. It's really cool stuff. Of course, you can't because of huge tidal forces that would rip you apart, but it would still be kind of cool. OK, when a giant star collapses to become a black hole, gravity is greatly increased at its surface, at its center, in all surrounding space, or all of the above. Where do we get an increase in gravity? At the center of any object, there is no gravity because of that object. In other words, think of it this way. If this is the Earth, let's say, and I go to the center, this piece of Earth is pulling on me this direction. This piece of Earth is pulling on me this direction. This piece is pulling on me here. There's a piece up here pulling me that way. There's a piece pulling me that way. Guess what happens to all those pieces? They cancel each other out. So at the center, no. At the center, you don't have any gravity to begin with. You don't have any gravity at the end. So it's not the center. At the surface, yeah, that's what we showed in that picture, right? How about in all surrounding space? Do we get an increase in gravity or not? You actually don't get an effect at all. Gravitation, it's tough to read that from here. You get only at the surface of the star as it's collapsing, because you're closer to the center, right? Gravitation increases at the surface. As the surface collapses at the same distance away, no change in gravity. So for instance, let's say the sun disappeared right now. 8 minutes later, we find out about it. Everybody goes crazy, right? But the sun disappears right now. It turns into a black hole. No more light. Just turns into a black hole. Do we get sucked into the sun? No, we don't get sucked into the sun, because black holes are not giant sucking machines. It's the same amount of gravity. OK, here's the sun. Here's the Earth right now. OK, let's say there's 10 to the 30th kilograms of mass. The sun becomes a black hole, and the Earth is still here. How much mass is there? 10 to the 30th kilograms. It's just in a tiny little space. How far are we from the center? Same distance. We continue orbiting just like normal. No more light. We freeze to death. But we don't change our orbit. Now, this isn't going to happen to our sun. Don't worry about it. But if it did, we would not be affected. No, it won't ever, actually. Our sun will become a white dwarf, but will never turn into a black hole. Not enough mass. Not enough mass.
It's not big enough to turn into a black hole?
Not big enough. Here we go. This is the exact question. If the sun collapsed to become a black hole, the orbit of the Earth would remain unchanged. Thank you. Okay. It's all about this F equals G m1 m2 divided by d squared law. Okay. Same thing. Okay. All right. Now, let's talk for a couple minutes on galaxies. Galaxies. This one happens to be the Milky Way galaxy. We are in that one. I heard the other day that it's really kind of disappointing. In Los Angeles, power outage in Los Angeles. 911 got a lot of calls about strange clouds above Los Angeles.
Strange?
Yes, very strange clouds. It was people looking up and seeing the Milky Way for the first time. They had no idea that the Milky Way, you could see the Milky Way when it was dark like that. Right? And if, by the way, if you haven't seen this, it's beautiful. I mean, it's amazing. This is amazing being on a ship and being dark and seeing this. If you go to the desert or you go far enough away, it's like going out to like Lake Assal in the middle of the night or something, right? You would see this sort of thing, right? You look up and it's like more stars than you can ever imagine, and you can totally see this like band of that. But if you live in LA, you're never going to see it, right? Because it's, pollution's part of it, but it's also, it's not just pollution, it's light pollution is what it is. There's so much light that even, at night, there's so much light around that you'll never see that many stars. So it's kind of sad. Okay. Different types of galaxies. There's these elliptical galaxies, which just look like ellipses. And by the way, galaxies are made of hundreds of billions of stars. In that like ellipse is 100 billion stars on average, right? You've got spiral galaxies, which look like kind of your typical galaxy picture. Different types of spiral galaxies. You've got barred spirals and different types of spirals, right? And then you've got irregular galaxies, which just don't have any particular shape at all. Okay. There are two irregular galaxies relatively close to us. I don't know what relatively means in this case, but many tens or hundreds of light years away, but still light years away. The Magellanic Clouds. They're just, they're millions of light years away? I think millions of light years away. Does it say?
About 150,000 light years.
150,000 light years away, okay. So those are the two Magellanic Clouds. They're near us, Magellanic Clouds. They were first described by the navigator on Ferdinand Magellan's ship. So that's when they were first described. So anyway, nearby. What's that? There, your GPS, John. This is a spiral galaxy called NGC 6744. If you look these numbers up online, you'll get lots of information about these things. We take lots of these pictures with like the Hubble Space Telescope and things like that. Galaxies are the largest, aren't the largest things in the universe, depending on how you define thing, right? You've got stars, you've got galaxies, okay? And then you've got clusters of galaxies. Okay, now, this is huge, huge, huge amount of space here. This is us in the Milky Way galaxy. 100 billion stars. This is Andromeda, the Andromeda galaxy, which is like 100 million, or maybe 200 million light years across, right? I think it might says it in there somewhere. There's another galaxy here called Triangulum, which is only named because it makes a triangle between us, Andromeda, and that. And then there's some other galaxies in here. There's the large and small, the large Magellanic Cloud here, et cetera, right? Now, in there is Earth and 100 billion stars. Our sun and 100 billion stars. Lots and 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 lots of stars. Same here, same here. This is called our local group. Okay. Now, our local group fits into a cluster. Okay? This yellow circle here is our local group. You can kind of see it's a triangle. It's hard to see from here. This, I lied on the size. This is only 10. This is only 10 million light years from here to here. Okay? 10 million light years. So you shoot a beam of light. 10 million years later, it goes like across our local group. Right? That's a long time. There's lots of other local groups in here. Okay? There's some way out here, some over here, some over here. This is called our local supercluster. Well, guess what? We've got networks of superclusters. So here's our little local group. Here are those two things we just saw. This is now 100 million light years, right? And look at all these other network, like superclusters. I mean, it's just an immense amount of space, right? By the way, here's an interesting fact. Let's say that a guy right about here, let's say 100 million light years, so here, here, about here, some dude happens to have a really, really, really powerful telescope. Doesn't exist, but let's say he did. And let's say he pointed it at Earth. Let's say somehow he could point it at Earth. And he looks at Earth. What's he looking at? Dinosaurs. Dinosaurs. Because it took that long for the light to get to him. Right? So he goes, oh, that planet down there doesn't look like there's any intelligent light. They've got these big lizards, but that's about it. Well, we've 65 million years later, we're still evolving, and hey, we can look back, right? So kind of cool stuff. The last chapter on Monday. We'll talk about some of this stuff. Okay, so guess what? Network of superclusters. Well, that's our little local supercluster. This is now 10 billion light years. And look at all these different like superclusters. I mean, that every little dot is one of those giant superclusters, which is made up of local clusters and local groups of hundreds of billions of stars. Hundreds of billions of stars in each one of those little dots. That's how tiny we are, really, right? That's how huge the observable universe is. We're not sure what's outside the observable universe. I mean, there might be other universes. I mean, it might be the fact that the universe is infinite. And if the universe is infinite, what would be really weird about that is that you guys could go somewhere, find another planet that's exactly like Earth, that has all 13 of us in the same, well, 11 of us today, in the same room, sitting there watching a video about the, local universe, or right, the observable universe. I mean, thinking about these things it's really amazing. But we are very tiny in the grand scheme of things. But so when you worry about something tonight, sleeping, right? Don't worry about that little tiny thing. Worry about the fact that we're a tiny little itty bitty dot in the observable universe. All right, we've got one more chapter on Monday. Tomorrow we have lab. We'll do something involving astronomy tomorrow, and I will see you then.